Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
The cosmos is full with secrets, extending from the backyard of our own solar system to the far-off beaches of the cosmic ocean. That's how it's always been, a spooky place full of mysteries and mysterious occurrences that will give you the chills. Now, on board Voyager 1, one of the most famous NASA spacecraft of the 20th century, strange things are happening in the vast emptiness of space, billions of miles from Earth. After 50 years of continuous flight, the most distant spacecraft ever built by humanity is still in operation. What's even more odd is that there are no indications of a malfunction or anything. NASA scientists are frantically attempting to determine the cause of this odd signal. What precisely has occurred, then? What may this terrifying signal entail for the rest of us here on Earth? Come us as we delve deeply into Voyager's historic journey to date, as well as the recent, horrifying signal in deep space that has baffled scientists and experts. Voyager 1, which was launched on September 5, 1977, was designed to map the outer solar system with a focus on the gas giant planets Jupiter and Saturn, as well as Titan, Saturn's moon. Launched in the same year as its twin, Voyager 2, it had a somewhat different mission to study the outer planets before reaching the end of the solar system. NASA was at its peak in those years. NASA had won the U.S. space race and successfully landed men on the moon a few years prior. The engineers at NASA were the world's envy. Both Voyagers had to travel through the asteroid belt, which is made up of rocks and junk circling the Sun, in order to reach Jupiter and Saturn. They had to withstand radiation from Jupiter, cosmic rays, and other space dangers. However, the two spacecraft arrived without any problems and started their extensive solar system trip. Many planetary scientists still rely on the unusual photos taken by the spacecraft's wide-angle and narrow-angle cameras, making their findings the stuff of folklore. Before the Voyager twins embarked on their amazing multi-decade journey of the large planets, mankind had only a rudimentary awareness of the solar system's far-off worlds, including Jupiter's tumultuous atmosphere, Saturn's shifting ring, Uranus' tilted axis, and Neptune's great dark spot. The profound findings opened our eyes to a universe never before seen. Voyagers 1 and 2 captured the outer solar system in all of its beauty through hundreds of photos, revealing it for the first time. 4 decades ago, early in their journey, the Voyagers stunned scientists with their first up-close pictures of Jupiter's and Saturn's moons, exposing the presence of active volcanoes and fractured ice fields on worlds that astronomers had assumed would be as crater-pocked and lifeless as our own moon. In particular, 546 days after launch, in March 1979, Voyager 1 arrived at Jupiter. In July of the same year, Voyager 2, which had a different course, arrived. The Vidicon cameras on board both spacecraft were built to be reliable platforms for generating full-color pictures through the employment of red, green, and blue filters. Their rotational velocity is more than 15 times slower than the crawl of a clock hand, so they rarely spin at all as they move across space, reducing the possibility of fuzzy pictures. The Voyagers captured almost 33,000 images of Jupiter and its satellites in total. It seems like each picture revealed something new. Rings around Jupiter. One of Jupiter's 53 known moons, Europa, has an ice covering that was shattered and believed to be more than 60 miles thick. A gravity assist gave the spacecraft a send-off push of 35,700 miles per hour as they exited the Jupiter system. They couldn't have escaped the Sun's gravitational pull and entered interstellar space without it. The Voyagers split off at Saturn. After dodging billions of dust grains as it navigated Saturn's rings, Voyager 1 passed Titan, an orange-shrouded moon, and continued northward out of the planet's orbit. Alone, Voyager 2 proceeded to Neptune and Uranus. Voyager 2 discovered 10 additional moons around Uranus in 1986, adding the planet to the expanding list of planets with rings. However, the Space Shuttle Challenger's premature explosion after launch eclipsed Voyager 2's discoveries, which came just 4 days after the spacecraft's closest approach to Uranus. The 7 members of the Challenger crew perished, among them Christa McAuliffe, a New Hampshire high school teacher who was slated to be the first civilian astronaut. After 3 years, Voyager 2 observed the fastest wind speeds of any planet in the solar system, reaching up to 1,000 miles per hour while cruising at a distance of around 2,800 miles above Neptune's blue methane atmosphere. Triton, the biggest moon of Neptune, has a surface temperature of -391 degrees Fahrenheit or -235 degrees Celsius, making it one of the solar system's coldest locations. 5 miles into the moon's atmosphere, nitrogen gas and powdered particles were ejected by ice volcanoes. If Carl Sagan hadn't been an astronomer on the Voyager 2 imaging crew, those pictures of Neptune and its moons would have been the last that either spacecraft took. After the official grand tour was over, NASA intended to switch off the cameras on both probes. The project had officially been renamed the Voyager Interstellar Project, although it had been prolonged in the hopes that the Voyagers would reach interstellar space. After Neptune, there would be nothing but the unending emptiness and seemingly far-off stars for picture opportunities. NASA authorities were pushed by Sagan to have Voyager 1 send out one more batch of photos. Thus, the probe pointed its cameras back toward the inner solar system on Valentine's Day of 1990 and captured 60 last images. Sagan's The Pale Blue, the most eerie of them all, saw Earth from a distance of 3.8 billion miles. It continues to be the farthest depiction of our planet ever captured. Earth is hardly visible in the picture, its brightness veiled by sunlight reflecting off the lens of the camera. It doesn't even take up a whole pixel. According to Spilker, Sagan put a lot of effort into persuading NASA that it was worthwhile to take a closer look at the pale blue dot and realize how little it actually was. Sagan passed away in 1996. Voyager 1 entered interstellar space on August 25, 2012, marking the passage through the heliopause, the boundary separating the Sun's solar wind, as a testament to the persistence and dedication of scientists such as Carl Sagan. Voyager 2 followed suit in 2018. The two spacecraft are currently speeding across the solar system's vast outer regions. To put it another way, astronomers could never have imagined the Voyagers, yet their incredible adventures are far from done. Voyager 1 is now the farthest human object from Earth, having traveled over 15 billion miles at a speed of about 38,000 miles per hour. Like an uncle who has been granted an exceptionally long life or an old automobile that keeps running, the robotic spaceship is an endless superachiever. It has attracted space enthusiasts worldwide in the process. NASA's famous spacecraft continues to transmit signals to Earth from billions of miles away in the depths of space, providing fresh perspectives on some of the major enigmas of interstellar travel. These days, both Voyagers are so distant from Earth that it takes about 23 hours for a one-way radio transmission traveling at the speed of light to reach Voyager 1, and more than 19 hours to reach Voyager 2. They advance by an additional 3 to 4 light seconds each day. NASA's Deep Space Network, a triad of monitoring complexes positioned all around the world that allow continuous contact with spacecraft while Earth spins, is their only means of connection with Earth. The Voyager's transmissions are getting progressively weaker as they move away from us over time and space. Even nonetheless, the murmurs have completely changed scientists' assumptions about what the Voyagers would discover when they began their interstellar trip. The scant observations from the Voyager mission have shown a complicated dynamic structure created by the interaction of the greater headwinds in the interstellar medium with the exhalations of our Sun. Both initially traveled across a zone known as the transitional heliopause border, where the interstellar medium and solar wind forces are delicately balancing each other out. The region beyond the heliopause is mostly unexplored, shaped by particle showers from the previous violent deaths of giant stars and galactic magnetic fields. The best way to describe our heliosphere is maybe as a windsock that, as our solar system passes through the Milky Way, extends a long, undulating tail behind it. On the other hand, it may resemble a straightforward bubble or anything in between these two scenarios, a croissant-shaped structure with two tapering trailing lobes. It's unknown right now, but one thing is for sure: most of the high-energy cosmic rays that bombard our region of the galaxy are blocked from reaching us by the heliosphere. These rays have the power to destroy the cellular machinery at the core of Earth's biosphere and change the climate on our brittle planet. Therefore, in a manner, the solution to the riddle of how life began on a little planet orbiting an ordinary yellow star may lie somewhere, almost unfathomably far away, at the uncharted boundaries of our solar system. Following this, more data from Voyager over the next years might include vital information on the universe's beginnings for life. But what is the potential duration of the Voyagers? Perhaps we can have the missions extended until the 2030s if all goes according to plan. It's the limit, it all relies on the power. However, the Voyager's adventures will carry on even after they are utterly silenced. Voyager 1 will reach Proxima Centauri, our closest neighbor star, in 16,700 years, followed by Voyager 2 3,600 years later. After that, they will spend millions of years circling the galaxy. Long after the heliosphere has vanished and our sun has disintegrated, they will still remain in the universe, essentially undamaged. Not to mention one dot of light blue. They might be able to deliver one last message throughout their journey. It won't be sent by radio, and if it is, it won't be heard by human beings. 2 recordings, another type of antiquated technology, are used to convey the message. These aren't your typical plastic ones, of course. They're composed of copper that has been gold-coated and sealed inside an aluminum shell. Images and sounds intended to provide a feel of the environment from which the Voyagers originated are encoded in the grooves of the so-called golden records. In addition to the sounds of crickets, rain, and a mother kissing her child, there are images of kids, dolphins, dancers, and sunsets. 90 minutes of music feature Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good. Jimmy Carter, the U.S. president at the time the Voyagers were launched, also says, "We cast this message into the cosmos. We hope someday, having solved the problems we face, to join a community of galactic civilizations." This record represents our hope and our determination and our goodwill in a vast and awesome universe. The golden records are noteworthy for having an extremely extended shelf life. According to some astounding calculations, the chances of the golden record surviving extend beyond both the probable extinction of humanity and the collision of the Milky Way with the nearby Andromeda Galaxy, past even the death of the majority of celebs. This implies that one of the greatest cosmic riddles may eventually be revealed through the archives of the Voyagers. Throughout the many years that mankind has been studying the universe, we are the first to know with certainty that there are planets galore among the stars beyond our sun. They are found in many different forms, and most of them are around the size of the Earth. However, we have not yet found any proof of extraterrestrial life. Is life in the universe easily starting and widespread, or is it extremely uncommon? However, answering one question just raises others, as with most scientific inquiries: which of these exoplanets, if any, are home to life? How long does life endure, and how fast does it begin? The Fermi paradox is the moniker given to the unsettling quiet of the cosmos. Where is everybody? Is a famous question made by physicist Enrico Fermi. The billions of years that the cosmos has existed provide sophisticated technological life forms plenty of time to transit the galaxy, even at sluggish speeds. Why then is the universe so silent? In the meanwhile, some of the variables in the hotly contested Drake equation, a series of numbers that might eventually indicate the number of sentient civilizations we should anticipate to find, have been filled in by exoplanet discoveries during the past 20 years. The majority of its parameters, such as the percentage of planets having life, intelligent life, and observable technology, are still undefined. However, the equation itself implies that we could find a solution eventually. Compared to Fermi's quiet, it seems at least a little more optimistic. The Drake equation was a significant scientific breakthrough when it was initially proposed, and it offers many fascinating insights. How many intelligent spacefaring civilizations exist in our galaxy today? Was one seemingly unanswerable question that was for the first time divided into a manageable number that we could imagine answering one at a time. The rate of star formation in the Milky Way, the proportion of stars with planets, the average number of potentially life-supporting planets around stars with planets, the percentage of potentially life-supporting planets that end up with life, the percentage of planets that have life and eventually develop intelligent life, the percentage of intelligently inhabited planets that emit detectable signals, and the duration of time that such civilizations continue to emit those signals are a few examples of the things we could measure or estimate. An estimate of the number of active civilizations that we may be able to identify today will result from multiplying all of those factors. But right away, we encounter a couple significant issues. First off, we actually know rather well the rate at which stars develop in the Milky Way because we have measured it. Unfortunately, you would end up with essentially no stars if you increased that star formation rate by the universe's age since the hot Big Bang. You would figure that throughout the course of our cosmic history, the Milky Way should have created a total of about 10 billion stars. I understand that while 10 billion may seem like a large figure, it actually represents just 2 to 3% of the estimated 400 billion stars in our galaxy. Luckily, the reason this approach of figuring out how many stars we've formed, which you would think would give you the entire number of stars in the galaxy, is so utterly incorrect is simple to see. The apparent explanation on the surface is that the rate of star creation has fluctuated over the course of the cosmos. In reality, scientists now know that stars did not develop in the first 200 million years or so of the universe's existence. Thus, we now know that star production peaked after rising for the first 3 billion years of the universe's history, then declined thereafter. We have likely seen star formation bursts locally when we have absorbed smaller satellite galaxies, and we may even be beginning to see another burst as the Magellanic Clouds and Andromeda pull on the gas, dust, and other neutral matter in our own galaxy through their gravitational pull. However, that is only the surface explanation for the Drake equation's current problems. The fundamental explanation is because the Drake equation was based on an assumption about the cosmos at the time it was proposed, which we now know is incorrect. It made the assumption that the cosmos was timeless and unchanging. The universe has not existed in a steady state, where it is unchanging over time, but rather has evolved from a hot, dense, energetic, and rapidly expanding state. A hot Big Bang that occurred over a finite duration in our cosmic past, as we discovered just a few years after Frank Drake first proposed his equation. Rather, a far more fruitful path would be to compute the quantities we can presently reasonably speak about, then proceed as responsibly as possible towards the enormous cosmic unknowns. In contrast to the circumstances that existed around 60 years ago, when the Drake equation was initially put forth, we currently possess a superb understanding of the nature of our universe, encompassing both the Milky Way and the local group. We know what the different populations of stars are that are out there, and we also know what kinds of processes lead to the formation of heavy elements, rocky planets, and the potential for complex chemistry and significant reactions, like the synthesis of energy-storing molecules from nothing more complex than the common building blocks and starlight. Additionally, a great deal of knowledge has been gained on the kinds and numbers of exoplanets, or planets orbiting stars other than our own. Only 30 years ago were we finding our first planets near stars other than the Sun. However, as of July 2024, there are around 5,700 verified exoplanets. Indeed, there exist biases in our data since we tend to identify the planets that are most easily detectable. However, we have mechanisms in place to compensate for these biases. We really have some wonderful data here in our present Milky Way that we can use instead of speculating about how many stars develop, how many have planets, how many planets per system have the potential for life, etc. We already know the number of stars, the distribution of star populations, the number of planets around each star, the proportion of planets with elements that may support sophisticated chemistry, and the number of planets that could support life. From this point of view, estimating the number of possibly habitable planets in our galaxy is really rather simple. Indeed, there are several methods in which we may carry out that computation to demonstrate the versatility of our knowledge base. 80% of the Milky Way's 400 billion stars are red dwarfs, 18% are similar to our Sun, and the remaining 1 or 2% are too large and too brief in life to be of any significance to life. To the best of our knowledge, each solar system has between 5 and 10 planets, of which 1 or 2 are thought to be in the dubious habitable zone surrounding each star. We estimate that 20% or so of the planets around Sun-like stars are Earth-sized, and that a higher proportion of planets orbiting more frequent red dwarf stars are terrestrial. The number of stars, 400 billion, the fraction of those planets that are Earth-like in size, 0.20, the number of expected potentially habitable zone planets per relevant star, 1.5, and the proportion of those planets that are Sun-like enough to support life, 0.18, can all be multiplied if we make the conservative assumption that red dwarf systems are not habitable at all, but Sun-like systems are. Next, we calculate that there may be 21.6 billion habitable planets in the Milky Way. Using so many major figures is pointless, 20 billion is plenty. Additionally, we must keep in mind that there are ambiguities in all of these figures. Just 200 billion stars, or half of our estimate, may exist. Although the amount is small, less than 10% for sure, some stars may not have enough metals, or what astronomers refer to as the heavy elements in the cosmos, for planets to support life. It is possible that certain stars lack planets, although this is a very tiny percentage, less than 20% to be exact. Add another 33% uncertainty to our estimate in case the habitable zone turns out to be wider or smaller than we initially believed. Furthermore, our sample of exoplanets at the lower end of the mass radius part has been inadequate. We're not sure how accurate our estimate of 20% Earth-like size is, so we'll allow for a 25% margin of error. Overall, the number of possibly habitable planets in the Milky Way may be as high as 50 billion, or it may be as low as 5 billion. That number might climb tenfold if red dwarf systems are also possibly habitable. However, many of the issues we have previously been concerned about are probably not very important in the long run. Examples include whether a planet has a major moon or not, whether it contains a planet similar to Jupiter in its stellar system, whether it is near or far from the galactic center, and whether it is a part of a singlet or multi-star system. Beyond that, though, there are still some very significant unknowns about which we know incredibly little about the universe. Asteroids, gas in the galactic center, outflows surrounding large newly formed stars, and even the atmospheres and surfaces of other planets and moons in our solar system are all known to contain the elements necessary for life. What percentage of possibly habitable planets, though, have all the necessary components yet life actually evolved from non-life? Carl Sagan stated that the amount he provided, 0.10%, in his initial Cosmos series was cautious. It's not always the case like that. Just because life emerged early in Earth's history does not imply that a sizable portion of planets genuinely have or have ever had life on them. Life might be challenging. The probability that life emerges from non-life might be close to 100%, 10%, 1%, 0.01%, or 1 in a million. How likely is it that life would have emerged and flourished on Earth if we could turn back time and start the planet over? It's amazing how ignorant we are. In a similar vein, how often does life actually emerge and then perish versus how frequently does it persist for many billions of years? How often does it stay in an extremely basic stage, incapable of becoming complex, differentiating, multicellular, or reproducing sexually? How frequently does life on Earth genuinely start to resemble itself at the beginning of the Cambrian explosion, even after billions of years? Once more, we have no idea how this might operate. It makes sense if you calculated that it happened 10% of the time. Yet 90% of the time, it also is. And in 0.11% of cases, it is. If we make a bold claim without any observational or experimental data to support it, we are just fooling ourselves. Moreover, we know that it took more than 500 million years for a species to emerge that would develop sophisticated technology, even after life on Earth became complex, differentiated, multicellular, and sexually reproducing. And that was probably just the product of pure luck. How frequently does that happen? Is this an uncommon enough event to be compared to winning the Powerball lottery 5 times in a row, or does this likelihood make more sense when expressed in percentages? Moreover, how long is that high-tech existence going to last? Is it ever able to develop into a multi-planet or even interplanetary society, or does it go from being highly developed to being extinct really quickly? Our current level of uncertainty is so great that it is quite plausible that humans may be the sole sentient species not just in the Milky Way but across the entire observable universe, which most likely has a star count greater than 1 trillion times that of our own galaxy. With reasonable confidence, we estimate that there are around 20 billion Earth-sized planets, assuming an Earth-like atmosphere, that are composed of elements comparable to our own and spaced far enough from their parent star to support liquid water on their surfaces. However, how can we connect with aliens if they are real? AI might be able to assist. The craze for AI has taken over our economy and is about to spread beyond Earth to invading spaceships as well. AI also holds the prospect of reevaluating long-held expectations for space travel, such as the discovery that humans are not alone in the universe, just like it does on Earth. The development of AI explains this goal. Large language models, or LLMs, are built on the Transformer Neural Network architecture, which was first introduced in 2017. These models, which are transforming our world, were trained on internet-scale datasets and include a wealth of human knowledge. The International Monetary Fund estimates that they will have an impact on over 40% of jobs worldwide. But can we actually interact with hypothetically sophisticated civilizations using this technology? To be honest, this is a bold and maybe dangerous concept elsewhere, as hostile aliens might abuse this knowledge. Nevertheless, considering recent findings, it's a conversation worth beginning. There are a plethora of exoplanets in our galaxy, as demonstrated by space observatories like Kepler and the Transiting Exoplanet Survey Satellite, TESS. At least 300 million of them are thought to resemble Earth and may contain liquid water. We think that there may be sophisticated civilizations on a few of these worlds that are interested in getting to know us and our ways. Smaller open-source language models, like Mistral AI's Mixel 88X22b and Meta's Llama 370b, would enable training with selected datasets for interplanetary communication. Llama 370b is typically 130 gigabytes in size, making it quite large to send error-free over light years. Nevertheless, we were able to compress it into a few megabytes without sacrificing its functionality thanks to a method known as quantization. It would enable the AI to function independently without an internet connection, which is vital for interplanetary communication. We have two main methods, assuming we wish to transmit these LLMs to extraterrestrials: radio transmission, which is wide and sluggish, and laser communication, which is directional and quick. NASA's Lunar Reconnaissance Orbiter can transmit data at up to 100 megabits per second downlink over radio. This indicates that sending the whole full-size Llama 370b model to the Moon would take around 30 minutes. Data speeds as high as 622 megabits per second have been reached by the Lunar Laser Communications demonstration, cutting the transmission time down to around 5 minutes. Overcoming the great distances between stars, signal attenuation, and existing technology limitations is necessary to contact intelligent civilizations beyond the Moon. NASA's Psyche mission, for example, has a prototype laser interplanetary communication system. It launched last year toward an asteroid that is rich in metal. A few hundred megabits per second is the data rate that laser technology has attained. But using present technology, interstellar communication would probably slow down to 100 bits per second, meaning it would take hundreds of years to convey an artificial intelligence to Alpha Centauri, our closest neighboring star system, which is located a little over 4 light-years from Earth. Alternatively, as was previously mentioned, we may send a carefully selected and smaller model in less than 20 years that would only be a few megabytes in size, making it a mission that is doable for mankind. It would produce noises, visuals, and text as well. Historians, philosophers, scholars, and other specialists should decide on its personality, substance, and tone in order to reflect mankind as a whole. Another strategy to boost transmission rates is to use stronger lasers. We could send a lot of data over many light years if, as one of the breakthrough efforts suggested, we combined numerous 10 kilowatts lasers to create a transmitter with a 100 gigawatts power. And very rapid interstellar communication system might be developed by utilizing the sun as a gravitational lens. According to a different cutting-edge proposal, beyond Pluto's orbit at 550 astronomical units, AU, or 82 billion miles, from the sun, we would require a laser-equipped spacecraft. A more traditional approach would be to outfit each space voyage with a basic ruggedized onboard computer that houses a carefully selected LLM and an interface for interacting with it. This digital time capsule method will honor the history of the analog Voyager golden record while also extending it organically. The meticulously chosen pictures, sounds, music, and words on the gold-plated copper disc were meant to tell extraterrestrials about the history of our planet. Sometime in the far future, an advanced civilization could come across a spaceship that is outfitted with an antiquated computer or receive a signal that instructs it to reconstruct its artificial intelligence. By indirectly communicating with these life forms, we may show them that we are not alone and that there was once a human civilization that was possibly still extant and not all that different from their own. It can also expose our past, our goals, and our essence as a technological race. Now is the moment to take use of our AI developments to usher in a new era of intergalactic communication. Our legacy will live on even if we do not, since we will be able to communicate with alien intelligences through the launch of carefully selected big language models into space. Do you enjoy this video? Please like and comment below. Turn on the notification bell to get notifications for videos like this.